Black holes are well known for their terrible potential and their never-ending appetite for anything unlucky enough to get too close. A white hole, which is its counterpart and equally as terrible, is something that few people are aware of. Since white holes have only ever been theoretically possible, the discovery of the first one by scientists has put an end to this. Now, what exactly are white holes? What distinguishes them from black holes? More significantly though, is Earth in danger from black holes? Let's delve into the terrifying white hole universe that has recently emerged as a result of recent scientific findings. There are many things in outer space that will try to kill you, making it a very dangerous place. Some will expose you to harmful radiation, while others will asphyxiate you with toxic gases. However, one particularly awful space object will suffocate you for all time. This would be the nightmare that is known as a black hole. The black hole's counterpart, a white hole, is just as terrifying. These two objects have many resemblances and differences, and understanding white holes, which is the subject of this video, requires an understanding of black holes. In space, a black hole is an area where gravity is so powerful that even light cannot escape. There are a staggering number of black holes. Some estimates put their number at 1 billion, and the Milky Way galaxy alone may have more than 100 million of them. Sagittarius A is a very large one that can be found at the center of our galaxy. Approximately 26,000 light-years from Earth, this enormous structure has a mass 4 million times than that of the Sun. White black holes have been known about for a while. We didn't get our first look at one until 2019. The Event Horizon Telescope recorded it. Scientists from all over the world were enthralled by the stunning image of the black hole at the center of M87 galaxy, which is about 55 million light-years away from our planet. The Milky Way Cygnus X1 black hole, also known as the Swan or Cygnus, was the first black hole ever found. In 1964, astronomers discovered the black hole for the first time when a sounding rocket discovered celestial X-ray sources. The Unicorn, the black hole that is 1,500 light-years from Earth, is the closest one. Now, what exactly causes black holes to form? Pay attention because we'll discuss something similar when we get to white holes. The size of a black hole is actually determined by how it forms. For instance, stellar black holes are small but deadly in comparison to other black holes. A star may collapse or fall into itself as it burns through the last of its fuel, while the larger star continues to contract until it forms a stellar black hole. Smaller stars with masses 3 times than that of the Sun will change into neutron stars or white dwarfs. This kind of black hole is small but extremely dense. For context, consider that a city-sized stellar black hole can contain 3 times the mass of the Sun. As a result, the dead star exerts a powerful gravitational pull on everything in its vicinity. Supermassive black holes are another possibility. They outnumber stellar black holes in the universe. Despite having the same diameter as the Sun, they can be millions or even billions of times heavier. Most galaxies have this type at their center. The formation of supermassive black holes has not been fully understood up to this point, but they are constantly gaining mass from the dust and gas around them. According to some theorists, they are created when hundreds or thousands of smaller black holes merge. Others claim that dark matter is how they are created. The intermediate black hole is a type of black hole that can develop as a result of repeated collisions between stars in a cluster. Larger black holes can, however, also be created when intermediate black holes merge together. You may be wondering at this point whether the Sun, a star, can become a black hole and what that might mean for the Earth. That would not be possible, which is actually good news. This is due to the Sun's lack of sufficient mass to cause its collapse into a black hole. When the Sun reaches the end of its lifespan in billions of years, it will turn into a red giant star, burn through its remaining fuel, and then eject its outer layers to become a glowing ring of gas known as a planetary nebula. The Sun will eventually be reduced to a cooling white dwarf star. What does a black hole look like? Given that it shares some characteristics with white holes, this component is also crucial. The singularity, along with the other outer and inner event horizons, make up black holes. The first one is the area surrounding the black hole's mouth, known as the event horizon. It is important because once through it, nothing can escape, not even light. You can simply kiss a particle goodbye once it crossed the event horizon. According to scientists, gravity is unchanged by the event horizon. The singularity is the area inside a black hole where the object's mass is located. The mass of the black hole is concentrated at that one location in space-time. Black holes are invisible to scientists, unlike stars and other celestial objects. Keep in mind that not even light can pass through it, but they are discovered by the radiation they emit as they ingest dust and gases. The dense gas and dust that surround the supermassive black holes at the center of the galaxy may shroud them, obscuring their telltale emissions and making it harder to find them. But there is a circumstance in which a black hole's location might be perceived. Sometimes, the objects drawn in by a black hole will hit the event horizon and bounce out rather than go inside the black hole itself. This results in bright jets of material moving at nearly relativistic speeds. Despite the black hole's continued concealment, these jets can be seen from a distance. The difference between white holes and black holes should now be clear to you. Consequently, nothing can enter a white hole, as opposed to nothing escaping from a black hole. Consider it a large-scale cosmic yin-yang, or more practically, consider that the edge of a black hole is a point of no return, whereas the edge of a white hole is a point of no admission. Recall that we stated that black holes and white holes share many characteristics. A white hole appears exactly like a black hole if you're in a spaceship, provided you are at a safe distance, of course. For instance, it could spin in addition to having a mass. A ring of gas and dust may also be seen accumulating around the event horizon. Yes, the event horizon that separates a white hole from the rest of the universe also exists. You will be able to tell the difference if you watch for a sufficient amount of time. A white hole will cause a belch, which a black hole cannot do. Though white holes can be thought of as a black hole that have experienced reverse time. White holes are some of the most unique objects in the universe, and what makes them so fascinating is that nothing from the outside can affect what is happening inside of them. Although black holes have received a lot of attention, recent research into white holes has also yielded many fascinating findings. However, some of this work goes the other way. That is, attempting to invalidate the existence of white holes. Why do these researchers assert that white holes are logically impossible to exist? Playing this video backward doesn't make any sense physically because a black hole cordons off its portion of space when a star condenses into a tiny volume. It would resemble an egg unscrambling itself if an event horizon burst into a functioning star. This practically breaks the statistical rule that the universe becomes more chaotic over time rather than more orderly. Furthermore, even if substantial white holes did develop, they most likely wouldn't last for very long. Any ejected matter would collide with the orbiting matter, causing the system to disintegrate into a black hole. White holes do exist though, for more compelling reasons. First, black holes may give rise to white holes. Sounds incredible due to the two's diametrically opposed modes of operation. Hear us out. Physicists have pondered how these black holes could shrink and die ever since Stephen Hawking discovered that they emit energy. If a black hole evaporates away, many wonder what happens to the internal record of everything it has ingested. This is one of the puzzling questions that must be addressed. General relativity asserts that information cannot be revealed, while quantum mechanics asserts that information cannot be eliminated. What a conundrum! But theoretical physicists have an alternative viewpoint that would explain the formation of white holes. He questions how a black hole perishes. We have no idea. Why do white holes form? Maybe a white hole is a death of a black hole. The two questions fit together nicely, but you have to go against the equations of a general relativity and the transition from one to the other. Doesn't that sound cool? Carlo Rovelli is credited with developing quantum loop gravity, an unsuccessful attempt to transcend general relativity by positing that space itself is made up of tiny Lego-like particles. He and the others describe a scenario where a black hole shrinks to the point where it no longer abides by the particle level laws of stars using the tools from this framework. The black hole might turn into a white hole if quantum randomness takes over. This white hole might only be the width of a human hair, but it will be concealing a vast interior that holds the data from everything it had consumed in its previous existence. The white hole may remain stable though to eventually spit out all the data gathered by its predecessor, since it will be too small to attract orbiting matter. This scenario has an intriguing conclusion because it predicts that billions or trillions of years from now, after all the stars have collapsed and the resulting black holes have withered, the universe will be dominated by white holes. Even at the most fundamental level, this means that we may be living in a white hole world because the Big Bang Theory, which describes the explosion of matter and energy, is a classic example of white hole behavior. According to one scientist, the geometry is practically mathematically identical in the two instances.